I'm going straight for the quick method, peeps. So, dy dx. I'm going to pretend that this bracket is just on its own. So I'm going to differentiate as though it were just an x. So my power would come in front. I would still have my bracket, and I would take one off the power. Yeah? I'm then going to multiply that by the derivative of what was in my bracket, which in this case is just 2. I'm then going to simplify if I can. Obviously that last one was way complicated, so I'm not going to do that. But this one I can, because I can multiply my 5 and 2, so this becomes 10 2x minus 3 to the power 4. Done. Okay? Next one, dy dx. Does anyone want to have a go at telling me what this one is? 3 in the front. Done. Okay. There's no easier, no simpler to multiply this bracket here by 3. If you wanted to write 6x plus 9 and then have this bracket to the power 2, you could. But as I say, it wouldn't be classed as simpler, and so you wouldn't have to do that. I don't know why I'm leaving so much space, because you really don't need that much space. Right.
One time we don't have to write a bunch of
I know, I'm sorry. Oh, please.
Please and thank you.
Now, this next one's a little bit different. And the problem comes because in a short while I'm going to talk to you about another kind of differentiation that involves fractions. Now, this question here has an expression to the power on the bottom. So what we would do with this one is we would treat it as though we had, like when we had 1 over x squared. What would we have to do if this had said 1 over x squared? We'd rewrite it, yeah? And what would happen to our power? It would become negative because it's come up the top. So we would first of all write this as x to the power 6 minus 2 all to the power negative 2. Obviously my 1 is still there, it's just a now secret 1 in front. Had that number been anything else, we would just have that number in the front of the bracket. So no, I haven't differentiated yet, which is why it's still called y. And now I'm going to use my chain rule to differentiate this function here. So dy dx, my power is negative, so you've got to have negative 2. Remember, taking 1 off makes it more negative. And then you're going to multiply that by the derivative of what's in the bracket, which is 6x to the 5. We could multiply these two together, so we could write negative 12x to the 5. But if you left it like this, I'm sure you would get a full marks. Okay, so we would rewrite an example when it's just one expression on the bottom. Okay, that's good. Yeah. All right, another rule. So that's a chain rule. So the chain rule is when you've got a function and something more crazy is happening to that function. So that function might have a power to it. We'll talk about some later where we've got some trig involved, but we're doing that at a later date. We also, in fact, we've already talked about it for the exponential and the logs, and we've actually used the chain rule without really knowing it. Okay, so what's happened is when we had things like, oh shush now, when we had things like e to the 2x squared plus 5, do you remember we differentiated it as though it was itself? We had e to the 2x squared plus 5. And then what did I say you had to do? Multiply the derivative, multiply by the derivative of what was different, yes? So we would multiply that by 4x. And that's exactly what we're doing here. That's that chain rule, yes? So we differentiated it pretending that this was just an x, so we had e to the function, and then we multiplied by the derivative of it. So we've actually been using the chain rule already without necessarily calling it the chain rule. Okay? But do you all appreciate that this kind of expression here follows that rule? Rather than e to the x, you've got e to the something crazy. So try and think something crazy, something different, in the same way that these questions here have a bracket to a power. It's something crazy to a power. It's not just an x. Okay. All right, I've rambled a bit more, so let's stop this one now.